In this video, I want to demonstrate the shape and spread and center of a sampling distribution of the sample mean y bar. And I'm going to do this in R. It's going to be a bit of a simulation of sorts. And so here's the main deal. Sampling distribution. It's a theoretical framework in which we are considering many samples, each of a certain size. And we want to think about all of the samples possible. In this demo, I'm only going to be able to look at 100 samples. I could do more, but I want to keep it manageable. Each of those samples is going to have a sample of size 81. So this is not all possible samples, but it's quite a few. So we've got 81, 81, 81, 81, 81. Okay. And the variable that this is representing, call it y, is coming from a normal distribution, and the mean and standard deviation of that distribution is 10 and 2 respectively. So mu equals 10, sigma equals 2, n for normal. And what we're going to do is I'm going to randomly select 100 samples. Each of them has 81 values in it, and they're all coming from this little scenario here. To kind of draw a little picture of this, right? This population is normally distributed. The center is 10. And we would know, for instance, from the empirical rule and using the z-table or p-norm, right? We know what probabilities to expect between 8 and 12, 6 and 14. Right? We kind of know what this looks like, population Y. What we're about to do is collect samples from this population. We're going to look at the 100 sample means. So I'm going to open up R and show you some code that I've used to accomplish this task. Okay, I've got R open and I've got some notes up here. You've already been briefed about this info. And what I'm about to do is create a data frame. There are going to be 100 samples, and so each column is a sample, and there's going to be 81 rows in each vector or each column. So I've got these specifications, and I'm about to create a data frame. I'm calling it whoa. Well, actually I'm going to call it whoa normal because we're going to do this twice. And you don't need to be too worried about all this code here. You can just know that I'm creating a data frame that simulates sampling from this population that is normal with those specs. Excellent. And maybe I can show you what whoa looks like. Now, it would be it's pretty big. So maybe I will do the head of, no, I'll do tail of whoa underscore normal. Oh, there's a lot there because there are 100 vectors. Here's the 100th one, here's the 99th one, 98. And you can see that each one of these vectors has 81 values in it, and they're all kind of hovering around 10. Okay, so there's whoa normal. What I need to do now is extract the mean of each of those vectors. So I've got some code here ready to do that, and this is called a for loop. You don't need to be too worried about it, but what I'm doing is for every vector, I'm getting the mean, and then I'm going to call it sample means. So I'm going to run this, should go off without a hitch. And now I've got a vector called sample means. Let's take a look at it. There should be 100 values in this vector called sample means because there were 100 samples. This is 100 means. And you might see here that these numbers are also hovering around 10, but you might even notice there's not as much variability in these values as there was from whoa. In whoa, right, there's a 13, we're going down to 7s, ooh, there's a 14, there's a lot more variability here because these are the individual observations, whereas the sample means are, well, means. I would like to discuss now how are these 100 sample means distributed. So we're going to describe the sampling distribution of the sample mean. Now the sampling distribution is all possible means. We're only dealing with 100, but hopefully that it will demonstrate the theoretical properties. Okay. The shape of these sample means should be approximately normal because each sample came from a normal population because population is normal. We know that from up here. Okay. What is the center? Okay, so we know what shape. Okay, so we know the shape. It should be normal. If I was to label this, I would label it not y, but y with a bar. Now let's talk about where the center is. Right, what number do we put right here? Green tick mark. Well, the mean of the sample means should equal the population mean. But our population mean here was a 10, so it should be 10. 10. Next up is the spread, the standard deviation of the sample means. Now this is not just sigma, but is inversely related to the sample size. But since we know that sigma was 2 and the sample size was 81, then we know the spread of these theoretical sample means. And that's approximately 0.22222. I could say that's equal to 0.2 with a bar. Okay. So if I was to draw this picture somewhat like the population, I would put a tick mark that was representing 10.22222. And over here, this would have to be 9.777777777. Okay. And I could put more tick marks here, but I'm running out of space. So you would notice that the spread here is a lot less because the spread is no longer a 2, that 2 applied to the population. The spread is incorporating that square root of the sample size, so it's a lot less. What I'd like to do now is go validate these values in R. We're not going to get these values exactly, but they will be approximately equal because we're dealing, again, with only 100 samples and not all of them. So I've got some code ready to go. Let's look at a histogram. And as expected, the shape of this histogram is bell-shaped, roughly normal. And we've got another tool under our belt to validate that, right? We've got the QQ plots. So since this is expected to be normally distributed, I'm expecting to see a straight line. Indeed, pretty close. Next, let's look at the mean and standard deviation of this distribution. We are expecting roughly a 10, woo-wee, and roughly 0.2222. That's pretty on point. Hopefully that helps with visualizing this new idea of sampling distributions. However, I would like to do another demonstration here where we absolutely need to utilize the central limit theorem. In this example, example 2, we are going to this time take samples from a population, just like earlier, 100 samples, size 81 each, but this time this distribution is going to be not normal, but skewed. A chi-square distribution is right skewed, usually, and chi-square distributions we're going to talk about in the future, and they have different characteristics, but they are usually right skewed, and they depend upon something called degrees of freedom. In this example, I'm sort of picking it out of nowhere, but I'm going to let this degrees of freedom be 6, and something we'll discuss in about 5 weeks, but the mean of this chi-square distribution is the same thing as that degrees of freedom, mu equals 6, and the standard deviation of which is the square root of 2 times 6, which is the square root of 12, which is approximately 3.464. Okay. So those are descriptors of this distribution. The mean is about a 6, and how spread out is it? 3.464 could be used. Okay. So again, I'm going to take 100 samples. I'm going to get 100 sample means, and then we'll discuss the shape, center, and spread of these sample means. Let me show you how I've got this cooking in R. Here are the notes that you've already been briefed on. This time, the data frame that I am generating, I am calling Whoa Skewed. There's going to be 100 vectors, each with 81, and I'm going to create this data frame. Watch it whip. Good. Again, I need to create a little vector that extracts those 100 sample means. Here it goes. This time I have named this vector sample means skewed, and there should be 100 values in it. Might as well take a look at it. Looks about right. A lot of numbers near 6, right? Near the mean. Cool. Next step is we're going to discuss the shape, the center, and the spread of these 100 sample means. The shape is expected not to be skewed like this, but because of the central limit theorem, we expect the shape to be approximately normal. because the sample size is greater than 30, which allows us to implement the central limit theorem. So that's interesting, right? Because this population started out skewed. Look at it. Look at you. However, when we have a sufficiently large sample size, our baseline is just 30 or more, then the sample means from the skewed distribution should be normal. Pretty interesting. Now let's talk about the center of these sample means. It should just be mu, but mu was a 6. So this mean is expected to be 6. Next is the spread, the standard deviation of these means should be the standard deviation of the population over square root sample size. And over here we've got square root of 12 over the square root of our sample size was 81. I know the square root of 81, but this whole quantity is about 0.384. Okay, so I'm going to go back to R. We're going to graph these sample means. They should look approximately normal, hopefully centered at 6 with a spread of about 0.38. Okay, let's do the hist of our sample means that are skewed from a skewed population. Oh, look at it. Isn't that great? Not right skewed, right? Not in any overwhelming fashion. Let's validate that with our QQ plots. Should be roughly a straight line. Oh, yes. Mean. We're expecting to see about a 6 when we crunch out the mean of these 100 sample means. Indeed, roughly 6, and the standard deviation should be about 0.38. How satisfying is that? Okay, so all in all, some take-home messages here, especially with the second example, is that the central limit theorem states even from non-normal populations, samples and thereby their sample means will be normal as long as you've got a sample size that is sufficiently large. Whew, okay. I hope that was kind of fun for you, and I will see you in the next video.